Yeah, I got you.
All right, can you see me in this view, from this view? How far do I go on the screen here? Okay. Now there'll be times I'll pause because I don't want to dump a 40-minute file onto YouTube in this case. So, Chapter 1 starts off with charting the heavens. Here. So we'll briefly look at our place in space. I'm going to very, very quickly glance over scientific theory and scientific method. If you don't know scientific theory and scientific method at this point, go home. You know, you've gotten this since you were in the 4th grade, so I'll move past that. We'll look at what we consider the obvious view. The obvious view is going to be walking outside, looking straight up. You've got a 360-degree circle, and you've got a 180-degree arc over your head in 3 dimensions. So because of that, that's what we consider our obvious view. And we'll talk about obvious views and how you can perceive the night sky versus what is actually out there. In other words, what's below the horizon, and very specifically what is beyond our normal scope of viewing. We'll look at Earth's orbital motion, motion of the moon, and the big part we're going to talk about today will be the measurement of distance, and then how they're actually done. So to set up what I like to call cleaning, I do what I call filling in the potholes. Everybody's got a road of knowledge. Some spots you know very well, some spots you maybe a little miss on it. So if what I'm giving you right now seems to be a little bit repetitive, or you knew this already, understand I'm going to get everybody up to a certain level so that by the time the class ends, thank you very much, by the time the class ends, you will have a base knowledge that everybody has here. So, basic stuff, obviously it's Earth. We don't occupy any particular special place in the universe. Now that's kind of obvious to us now, but when you look at astronomy from an historical perspective, we used to believe that we were the center of the universe and that all things orbited around us. And that was a purview we had for almost 2,000 years, until we had people like Copernicus and Kepler and Galileo, who came along and altered our perception of ourselves. And in altering the perception of ourselves, it completely alters the perception of science. The universe is defined as the totality of all space, time, matter, and energy. Basically, it is absolutely everything. Sometimes you'll see a little chart at the bottom of the picture. This particular textbook company does this. What it is showing you is a wavelength. The wavelength in this case is light. The letters underneath it represent radio, infrared, visible, ultraviolet, X-ray, and gamma ray. And I'll have a color representing which one. So in this case, it is a picture of the Earth. It is in what we consider eye normal view. When we study science and we look at scientific tools and scientific measurement, all we are really doing is enhancing our senses. If you think of every single piece of technology that we have, every single scientific instrument that we use, all they are doing is enhancing one of our 5 senses. In astronomy, it happens to be almost exclusively visual. So in this case, you have to understand about the electromagnetic spectrum, which we'll cover in a couple of weeks, the different tools that are used to measure the electromagnetic spectrum and give us different insights into sciences. But basically, all it's really doing is it is enhancing these. So in this case, we're looking at the visible spectrum of light. You can see this is a picture of the planet Earth, looking at it from the central to South Pacific. Astronomy, of course, is our study of the universe. Anything that says O-M-Y means a study of. So does O-L-O-G-Y as in ology is also a study of. Astro being space. It is the first, the last, and the biggest study in science we have. Before we started looking at life, or gravity, or physics, or chemistry, as a civilization, we looked at the stars. We did it before we had the written word, when it was only oral tradition. Before there was banded people together in small communities to make the beginnings of civilization. We were looking at the stars, and we're wondering where we came from. So that's what the study of astronomy does for us. We're going to talk about scales. We're going to be talking about the very, very big in this case. In fact, the term we always see it on television, it's an astronomically huge sail, or it's an astronomical deal, or it's astronomically important. Well, they're trying to show you in their own way that it is a very, very big, almost unimaginably big measurement. So we're going to be looking at very, very large measurements, and we're going to have to distill those down into something that we can understand. When you study astronomy, we have a list of ages at which we can introduce different topics. Do you ever notice that multiplication starts in 2nd grade or 3rd grade? Why didn't it start in kindergarten? Why didn't it start in 6th grade? You ever notice algebra? You don't pick up algebra until 6th, 7th, 8th grade and the 9th grade. Why not in the 2nd grade? The reason is the human brain has a hard time understanding concepts until the brain physically grows to a certain level. Of every single study, the study is called psychometrics, and they have what are called psychometricians, get paid a fortune. Go out to college, get a degree, become a psychometrician, get yourself a job in an education company, you can write your own check. There's absolutely huge and very, very hard field and a very, very difficult field to get your degree in, but they're out there. Psychometricians say out of every single topic, whether it's addition, subtraction, whether it's adverbs, whether it's the War of 1812, whether it's poetry or art, the very last one on the list is astronomy. Because we're being asked to comprehend something that is so grand that it makes us insignificant. And not just the person us, but the entire civilization and the entire planet and the entire solar system. They are immeasurably small against the immeasurably huge. So it's one of the reasons why we offer astronomy as a senior level class, because we know the 17, the 18, and the 19-year-old person, their brain is just physically entering a developmental stage where they can truly understand what astronomy really is and what it's all about. So, not trying to make this over dramatic, but understand that astronomy is a universally important study. It's not only a study of what's out there, it's a study of what's in here. Because the first question we ask, and the first question we're going to explore after we start talking about distances and understanding distances is, why are we here, how did we get here, and where are we going? And that's a big part of astronomy. Now, some facts. Our galaxy, which we call the Milky Way galaxy, is 100,000 light years across. And we can toss around numbers and say, oh, 100,000 light years, or 1,000,000 light years, or 1,000,000,000 light years, or whatever happens to be here. We toss them around like they're nothing. We almost have to. Because if we ever sat down to try to really, truly comprehend what a distance it actually is, it could blow your mind. And I've seen people in class go, oh my God, I finally get it, and they'll sit in class and they'll hyperventilate. I've seen it in college classes where you teach a class and all of a sudden their brain understands what they're trying to wrap itself around here. So for instance, this is 1,000 quadrillion kilometers. Be interested to see what that actually writes out if you put out how many zeros it was. You'd actually literally go into scientific notation because there's so many zeros that you almost have to. But we toss it around like it's nothing. It's 100,000 light years across. It's about 50,000 light years deep. It takes 250,000 years for our star to orbit the Milky Way galaxy. As I tell all my science classes, there are two things that help you succeed in science. Number one is to follow the rules. The rules are nothing more than explanations passed on from antiquity till today to help us explain number two. Number two is follow the patterns. And you're going to find that looking at something simple like this swirling motion is going to be played out at different scales. Our solar system goes around the Milky Way galaxy. The same way our planet goes around its own sun. The same way the moon goes around the Earth. The same way that the solar system was originally formed. It's a consistent pattern. Once you find that pattern, a lot of the mystery of science goes away. The universe is an orderly place. It's got a very definite pattern. It's got a very definite behavior. It's extremely complex, and very few people really truly grasp it on a level where they can follow and say A is going to happen, B is going to happen, C is going to happen, D is going to happen, therefore E, F, and G will happen also. But it's there. One of the things I want you to look up when you get a chance to go home tonight, I want you to look up the term fractal. And the person, the man's name is Mandelbrot. Mandelbrot was a mathematician who invented what's called a fractal. A fractal is a geometric formula and pattern that nature grows in. If you look at a tree, look at a leaf on a tree, a leaf of a tree is a fractal because it branches out, and off of each branch something branches out, off of each branch something branches out. And that's the way the universe grows and works. If you can understand that pattern, you can master what's probably going to happen, which is one of the reasons why we've had so many advances in science once we understood those two rules. Follow the rules, or find the rules, or define the rules, and look for the patterns. I'm going to skip real quickly past scientific theories. I told you before you've done this, but let's real quickly. It's got to be testable, continually tested, must be simple, should be elegant. There's a man called Sir William of Ockham. Sir William of Ockham was an English friar back in the 1300s. And basically he came up with a bunch of rules, and one of the rules he came up with something called Occam's razor. And the rule is very, very simple. Given all possible solutions to a problem, it is almost always going to be the simplest solution is the correct one. And we're going to apply Occam's razor in a bunch of places, including orbital motion, how the Earth was formed, how the universe was formed. Simple solution is almost always going to be the correct one. Observation leads to theory. Theory leads to predictions. Predictions come back to observations. It's a constant cycle. Again, I'm not going to go crazy with this. This is something that is a tool that is being used constantly in these cases. So what's the obvious view? Obvious view is the night sky. Actually, let me turn the lights a little down. Actually, let's turn this a little better here. This is a shot. Yes, ma'am. Yes, you can. This is a shot of Orion's, the constellation of Orion. Now, looking at this, what do you see about it that's unusual? Yes?
The belt.
You see the belt, you see these three stars in a line here. Anything else about it? What's different in the picture here? Give me somebody else here. What do you think? What's different about that picture? What's unusual, or something you wouldn't really have seen before, or you might not have noticed if you're looking at the night sky? And actually, in this case, if it's Orion, you see it when you get up in the morning. Right now, if you get up about 5, 6 o'clock in the morning, I don't know what time you guys get out of bed at, but if the sun is still not up yet, look at the southern sky. It's going to be staring back at you. What do you see?
The orange star.
You see an orange star.
Beetlejuice.
That's Beetlejuice. And yes, they named the movie after the star, not the star after the movie. Orion's, this is called Orion's Nebula and Orion's Scabbard. All of this paints a mystical picture, according to the Greeks, of Orion the Hunter. But more, we'll backtrack that because we're going to go into a little bit about the culture and our observations in the sky and how they came to be what they are. At any given time, you can see about 3,000 stars in the night sky, unless you live in New Jersey. And it's not the air pollution that makes it hard to see, it's what's called light pollution. We are in what's called the East Coast megapolis. When you combine the lights of New York City, Jersey City, Newark, Philadelphia, Boston, and Washington, it gives off the most light pollution of any part of the world. So instead of us seeing about 3,000 stars in the night sky, we see between 1,600 and 1,700 in a given night. So you go out to western Pennsylvania, the Ohio Valley, Arizona, Wyoming. You will see so much more out there that you'll never see here unless there's a huge blackout and the entire East Coast is blacked out. And you need to have really the entire East Coast. They've had times when New York City's gone to blackout, and the very first thing people do is they grab the telescopes and they run up to the top of the skyscrapers and they plop telescopes down so they can look at the night sky that they couldn't look at before. It's one of the wildest things you ever see. You see people running upstairs with big tubes on their arms, racing to the top of the skyscraper because, of course, you can't use the elevators, the power's out. So they have to go up there and they do a lot of observations. But you'll never see the Milky Way in the night sky. You'll never see that headlong view of the Milky Way galaxy that other parts of the country do unless the entire East Coast goes blackout. If that's the case, you'll be able to look up, you'll see this large, long band, almost looks like a cloud. It looks like a milky white streak that goes to the sky, and that's what gives us the name of our own galaxy, the Milky Way. Human brain tends to find patterns. I'm an old Star Wars fan. So you know what I see here? I see an X-Wing fighter turn on its side. That's my one I see there. But of course, Orion the Hunter is a big one you see here. And that's what people predicted. They see a picture of Orion with his belt and his scabbard. Here is his shoulder, the mighty club being raised, his shield. He is fighting Taurus the Bull. And Taurus the Bull is in the middle of a battle, and Orion can never be defeated except by his heel. The same way Achilles had that weak heel here. Well, coming along in the lower part of the night sky is the constellation Scorpio. And Scorpio, according to the story, while Orion was battling Taurus, Scorpio came by and stung him, and Orion died because of it. And that was the legend born of the constellation of the Bull, which is going to be up here in the sky. Then you have Orion, which is here, and then you have Scorpio, which happens to be down here, and human imagination put this together here. Polaris, the North Star, is a navigation star. We're going to use that a lot here. It's just coincidental that the North Pole almost directly points at it. Polaris is 90 degrees in the night sky. We'll talk another day about locations in the sky, but on a 90-degree angle going straight up is where our north is. Well, in this case, on the top of the Earth. Polaris is at 89.5 degrees, excuse me, and then Polaris itself would come off by half a degree. So any given time of the year, looking northwards, you can always spot Polaris. You can also determine where you are on the planet latitude-wise, because if you measure the angle from Polaris to your chest to the horizon, you'll get an angle out of that, and that angle is where you are on the Earth. If you look at the night sky tonight and go to 42.5 degrees, and you look at 42.5 degrees, that's where Polaris is going to be. Why? Because we're at 42.5 degrees north of the equator. So there's a lot of useful stuff for this. What's not so useful, and I don't like to call it useless because there are religions that use astrology, which is to take those patterns in the sky and make predictions based upon them. So I prefer to say if somebody wants to call it a science, I'll disagree with them. I'll say you're false on that. But will I say it's not valid? No, because many people believe in it. There are many religions that believe in it, and I would never want to disrespect the religion, but it's based upon faith and belief. And faith and belief is a very, very powerful part of the forces of nature in civilized society. But as far as a science, a true science goes, it does not match up to it. You cannot test it against any standard scientific procedure and have it stand up as anything but completely random in most cases. Now looking at Orion, just because it's all flat against your eye at the night sky, just because you see this pattern here, does not mean they're all sitting at the same distance. They're actually sitting at various distances from each other. As you can see from this diagram, some of these are very, very far distant. For example, the 3 stars of Orion's belt are called Alnitak, Alnilam, and Mintaka. They're all, most star terms are names that are Arabic in origin. So those are it's Alnitak, Alnilam, Mintaka. If you look at Alnilam, look how much further away Alnilam is versus Alnitak is versus Alnitak, Alnilam, and Mintaka. You see the distances of the 3 of them. You can see that big red star we talked about a moment ago, look how close it is compared to the other ones here. So just understand that when we see a field and we see images in the sky, that all the stars are going to be at different depths. That's a definite. We have what's called the celestial sphere. The celestial sphere is what we perceive from the Earth looking at the night sky. We have stars that are hung onto this crystal sphere, according to Aristotle and to early scientists in the times of antiquity. These patterns are actually placed onto this sphere. There are 88 of them. We have a use for them now because we use them like map coordinates. And if I said there was a supernova in the constellation of Taurus, and there wasn't in 1066, I would know where to train my telescope to find out where it is in the sky by using it like it's a map, like the states of the United States. If there was an explosion in Ohio and I want to put a satellite on it, I'd take the camera and I know where to basically swivel on the United States. I would be looking in California, I wouldn't be looking in Mexico, I wouldn't be looking in Maine. I'd have an idea where I'm supposed to be. Same thing happens with the coordinates. These are 2-dimensional to us because we can't see that 3rd dimension depth because it's so far away. The Greeks almost figured this out. They actually said, you know something? This might not be the way it was, but the problem was they couldn't wrap their own brains around these kinds of distances. The universe can't be that big. These distances can't be that far. Some people actually mathematically figured this back in the time of Aristotle, but they were dismissed because they couldn't grasp the idea, or they weren't willing to grasp the idea of the universe being that large, so they fell back to the next best answer. Occam's razor wasn't applied. It fell back to the second one, which was, it's all hung on a crystal sphere. This was adopted by the political and religious powers of the time, and you had 2,000 years, or almost 2,000 years of belief in the Earth being the center of the universe, and everything goes around it. Now to break up measurements, 360 degrees is a circle. If you break up that 360 degrees into 60 basic broken down equal pieces, they are called minutes. So 360 degrees inside of 1 degree are 60 minutes. Take one of those minutes, you can break that down by 60, and it's measured in seconds. So when we measure distance and locations, it's degree, minutes, seconds. Now before we had computer measurements, before we had a lot of technology, the telescope came along and really helped us out here. There were people, one of them being Tycho Brahe, was a master of using celestial coordinates and measuring celestial coordinates to the degree, minute, and seconds with the naked eye, which is really an accomplishment. But considering they had nothing else to work with until Galileo grabbed Hans Lippershey's polished glasses, stuck them in a tube and pointed at the sky and made a telescope, we didn't have those kind of measurements. So we have degrees, we have minutes, we have seconds. You can see on here, 360 degrees. You take 1 degree off of that 360 degrees. You break it into 60 minutes. Break off the 60 minutes, you get 1 second. So in 1 degree second in the sky, if you were to put a ruler to the sky, 1 second is less than a millimeter on the sky. To give you an idea, if you were to hold your finger up, just take your pinky and hold it up to the sky, that's going to be about a minute. You take your hand, you splay your hand, I believe it's 15 degrees between your thumb and your pinky. One finger, your thick middle finger, your index finger is degree, and then 1/60 of that's going to be a second. So it tells you how accurate you can get with degrees, minutes, and seconds. Noon to noon is called a diurnal motion. This is a solar day. People are going to start talking about days versus solar days. We'll talk a little bit about that next week. Understand that when you measure from 12 noon to 12 noon, that is considered a solar day. It's not from the rising or the setting of the sun. They use 12 noon straight up. And the reason why was because one of the things that ancient people did is they measured shadows. A sundial was nothing more than a measure of shadow. So when you didn't have a clock, you had a sundial. And the sundial was measured off the motion going around the sun. Stars aren't quite in the exact same position 24 hours later. There is a slight shift. Why? Because the rotation of the Earth has nothing to do with time. We make time our own construct. It's our own measurement. And the rotation just doesn't cooperate. It's somewhere in the neighborhood of, I think it's 23 hours, 59 minutes, and 34 seconds. Is the actual rotation time. It's not 24 hours. Now for us, 24 hours, that's not a big deal. But when you start measuring against the sky, and you start seeing a cumulative effect of change in motion, that's how they pick up on that. And this is, so the Earth, due to the rotation of the sun, where they are once again in the same place, this is a single sidereal day. So a sidereal day is just a smidge more than a solar day is. And that's going to come into effect because when we measure things like the rising and the setting of the moon, or where things are located in the sky, we have to understand that there are slight changes. There's a difference between a solar and a sidereal day. Just understand there's an amount of time difference on that. That's what we're trying to talk to you about. So as you're going along, not just a single day, but not just a week, not just a month, but 3 and 4 months, you'll see a shift and a change in the night sky. So pretend that I am the Earth. And as this projector's hitting me right now, that's the sun. I'm looking at the sun. It's daytime. If I had eyes in the back of my head and I'm looking behind me, that's the night sky. So as I go through, now watch my motion here. Now watch where my eyes in my back of my head are, right near the face of the screen. As I go through September and into October, am I pointed at the same spot again? No. As I continue going all the way around the sun with always day and night, so here's day again. Let's come over here. In this case, I'm looking off this side here. My back of my head is looking at a different spot. You get a different view of the night sky. That's how this works. So that's the reason why, as you're going around the sun, you get different images. Now, we've made names for those different images. I'll try to get through as quick as I can. We have 12 constellations that the sun passes through. So as an example here, I'll say that, once again, the projector is the sun, and I'm standing here. Let's say it's October, late October. My birthday's late October, so I know that constellation. I am a Scorpio. What that means is if I were to look through the path of the sun to this night sky and back of me, the constellation Scorpio is there. So the sun will pass through. So I'm looking at where's October right here. Oh, there it is. Okay. So if I'm sitting here and I look through the sun, I see the constellation Scorpio. This is what's called the zodiac. This is the path that the sun goes through during the 12 months of the year. Ironically, there really aren't 12 constellations. There are really 13 of them. There's another one out there that it sits right between Scorpio and Sagittarius. Name flew out of my head. I'll get it another time here. But basically, a true Scorpio is really from October 23rd to like November 4th. And then this other constellation, because in this case, Scorpio doesn't sit this way in the sky, it sits this way. So it passes through Scorpio very, very quickly. But then they go to the next constellation. Yes?
Isn't it like Ophiuchus?
Ophiuchus, that's Ophiuchus, that's right. Thank you. So Ophiuchus goes for most of it. Yes?
I was going to say the same thing.
Okay, so, and that gives you like from November 4th or 5th to like November 22nd. So while you're Scorpio, you're really kind of Iphicus. There's only like a few true Scorpios like me. I'm October 24th. I'm a true Scorpio here. But basically, it's the path that the sun takes so that when you are born, if you're born like October 24th like myself, the sun was right smack dab in the middle of the constellation Scorpio. You get that's your zodiac sign. Now then astrology tax on, well, if you're a Scorpio, you have characteristic A, B, C, D, and E, and this is going to happen today, this is going to happen tomorrow, this is going to happen the next day, and that's where science really tests it and it doesn't hold up. If you ever read a horoscope, it doesn't tell you what's going to happen. It tells you what you should do. And that can really apply to every single one of them. It doesn't say, watch out for yellow cars today so that I walk outside and get run over by a taxi cab. So it'll say things like, be vigilant with friends and be positive in the work environment. They give these things they tell you to do as opposed to watch out for falling rocks. You know, so you're working, a brick falls, hits you in the head or something along those lines. So I'm going to wrap it up there. If you can kill that for me, I'd appreciate it. I'm going to wrap it up there. Here's what I need for you